My name is Brian Wade, and what we're going to discuss today are some things that I have seen in recent MONWRITE data that I thought would be appropriate to share in a conference kind of setting. The title of the presentation is What's Going Wrong, LPAR Weights, and so let's take a look at some of these things. Here's the abstract. In my job, I often look at MONWRITE data from client systems, and recently I've seen a rash of data that show me CPCs where the LPAR weights weren't set correctly. There are some consequences here, and so I want to go over them. In this presentation, I review basic concepts about LPAR weight, notion of entitlement, and how to recognize config problems and so on. So here's the agenda for today. I want to look at some basic concepts around LPAR weight, entitlement, polarization. There are ways for things to go wrong. We have problems and some solutions to show you about. I want to show you some techniques related to suggested practices for how to manage LPAR weights. And then I want to show you some tools that might help you in all of those things. And then we'll summarize. So let's just take a look at some basic concepts related to LPAR weight. And this chart tried to explain exactly what LPAR weights are all about. In any kind of a system where there's only a finite amount of resource to go around, the arbiter for handing out that resource needs to be informed of some scheme of what to do if there's more demand on the system than there is actual capacity to give out. You might recognize rationing as being a scheme that gives out, say, water according to some rationing scheme. Prism Hypervisor has the same kind of thing. The purpose of LPAR weights is to tell Prism how to hand out CPU power when there is more demand for CPU power than there is power available to hand out. So the Prism Hypervisor distributes computing power to the LPARs it's managing, and these numbers called the LPAR weights control how much power each LPAR is guaranteed to be able to use whenever it wants. In other words, these weights inform Prism of how to compromise when there's not enough to go around. Now, any of you who have ever shared a closet, a clothing closet with somebody else are very well familiar with the notion of weight. Let's say you're sharing with one other person and you agree that each of you is entitled to half of that clothes bar in the closet, half of that closet space. That half represents your entitlement. So we might say that each of your weights are equal. You are allowed to use more than your half as long as your partner wants to use less than half. But when your partner's demand increases and your partner wants to use that half, you have to back off. And that's exactly how LPAR weights work. As long as the demand is far less than what's available, partitions can use what they want. But when push comes to shove and the demand is so high that we need to make compromises, the partitions are allowed to use power according to their weights. So here I've got in the middle of the screen Fred, Barney, Wilma, and Betty, the names of 4 partitions, and the weights for them. Fred's weight 100, Barney's weight 40, and so on. If we add up those weights, the sum of those weights is 280. And we can compute each partition's percentage guarantee of the total power by taking Betty's weight and dividing by the sum of the weights, multiplying by 100, and that gives us a percent. So what this chart is trying to illustrate is that Betty is entitled to use 26.8% of the total power whenever Betty wants to. There's certainly no obligation for Betty to use that power, and moreover, if Betty's demand is light, much less than 26.8% of the total power, then the other partitions can eat into Betty's entitlement, just like I described with the example with the clothing closet a few minutes ago. So this is the notion of LPAR weight, and you notice the sum of the weights is very important. So where do we set these LPAR weights? If we haven't activated the partition yet, then the place where we set the weight is in a place called the image activation profile. And I've included a clip here from an HMC in our lab. You can see that we're working with the image profile for this partition called AST1. And right here, this blank where the red arrow points to, that's where we set the weight for partition AST1. Now, if the partition has more than one processor type in it, if it's a ZVM mode LPAR, then there's a weight for each type. And you should keep that in mind if you have heterogeneous LPARs, or what we sometimes call mixed engine LPARs. So when you activate AST1, this is the weight that AST1 will start light with, a weight of 50. If the partitions are already up on your KEC, then the way that you set them is on a screen called Change Logical Partition Controls. This is a screenshot of that particular screen from the HMC, and you can see that the names of the LPARs are all listed down here on the left-hand side, and you can see that each one of their weights appears too. You can see further that these are input boxes. This is a place where you can type in a number and make a change. So if you wanted to juggle or fine-tune the weights of these various partitions, you can put the changes right into these boxes, and then you click what's called Save and Change. I put this red caption right here to draw your attention to this button. Save and Change saves all of your updates to the various image activation profiles and also changes the running systems. So this is a way that you can make a tuning adjustment to partition weights on the fly without having to take partitions down and bring them back up again. There's no need to do any of that. You just use Change LPAR controls, and voila, you can make changes to the weights. So I want to talk now about the notion of entitlement. I've alluded to it somewhat where I drew the pie graph and I said Betty was entitled to 26% of the physical power whenever that partition wanted to draw. I talked about the notion of the divided clothing closet and each partner being entitled to use half of that hang-up bar there in the closet. That very much describes the notion of entitlement. For partitions, when we talk about entitlement, what we mean is the amount of core power that the partition is allowed to use whenever it wants. And we do those calculations just as I illustrated a little bit back. We use the number of shared cores, we use the LPAR's weight, and the sum of the weights. We usually express these in units of cores worth of power, which I'll explain with this table. Let's say we have 45 shared cores. We could imagine that they're IFL cores. 45 shared IFL cores, and we've got 4 partitions, Fred, Barney, Wilma, and Betty, with weights as I illustrated previously. The sum is 280. These percentages in the percent of sum category or column are exactly the sizes of those pies from the pie graph a few charts back, and you'll notice that the percentages add up to 100%. The entitlement is that percent times the amount of shared core power available. So 35% of 45 cores would be 16.1 cores worth of power. 14% of 45 cores is 6.4 cores worth of power, and so on. You notice if you add up all of these numbers, you get 45, which is the number of shared cores available. So this second column is the percents, as I indicated in the pie graph a little while back, and then the entitlement is the amount of core power that the partition is allowed to use whenever it wants. You're going to see that the entitlement and the number of logical cores defined for the partition are closely related. As we go through this presentation, you're going to see that pretty clearly. So here's the formula for calculating the entitlement for Fred. I have the 45 shared cores. I have Fred's weight divided by the sum of the weight, and that gave us 16.1 cores worth of power. Many analysts, myself included, usually write that as 1607%. You'll notice there was a rounding thing going on here. We usually write that as 1607, and that means 16 cores worth of power. A value of 100 usually represents 1 core. So that's what we have for the notion of entitlement, and we're going to talk a lot more about entitlement as we go on through this presentation. So what does PRISM do with that entitlement? What it does is it spreads that entitlement over the logical cores defined for the partition. You might think that every logical core is entitled to the same amount of power. In partition Fred, for example, you might think that Fred's entitled to 16 cores worth of power, and that's evenly spread over all the logical cores defined, but that's not the case. In what PRISM does in vertical mode, and everybody runs in vertical mode nowadays, or at least most people do, PRISM tries to do what I call entitlement packing. In other words, it packs the entitlement onto pretty much the fewest number of logical cores for the partition that it can. And the reason that it does this is for topology reasons and ultimately for cache reasons. We're trying to get the most out of the memory cache. So what do the bullets say over here on the left-hand side? PRISM spreads the entitlement unevenly over the logical cores. I've drawn a picture here. I showed in this table that Wilma has entitlement to a little over 10 cores worth of power, but has actually 20 cores defined for the partition. Back on that image activation profile, when we said how many processors, we configured 20 there. I should warn you that even though the image activation profile says processors, you're really configuring cores there. So Wilma has a little over 10 cores worth of entitlement, but 20 logical cores. And so what that ends up with is PRISM does the packing like this. 9 logical cores are completely entitled. We call those vertical highs, and that's what this column says. That's what that column represents, that notation. VH means vertical highs. Those logical cores are completely entitled. They are allowed to use as much power as they want whenever they want. And moreover, Prism always returns them to the same physical core in the topology. That's really nice for cache reasons. So we have 900 so far used up by the 9 VHs, and then to use up that remaining 144, Prism makes 2 mediums with entitlements of about 72, and then that makes 11 cores so far, and then 9 left over. So what I've got here are 9 vertical lows entitled to nothing, 2 vertical mediums, each one entitled to about 72% of a physical core, and then 9 physical cores that are completely entitled. So what this creates for the operating system running in the partition, like ZVM control program, for example, or ZOS or whatever, is a lot of incentive for the partition to run its work on only its entitled cores. We want the operating system running in the partition not to try to run on the vertical lows. If it's at all possible, it should cram its workload into the entitled logical cores. And the reason for that is cores out here, vertical lows that are entitled to nothing, they are at risk for Prism not running them unless there's spare power. These are the places where you're guaranteed to be able to run. These logical cores are not guaranteed even a drop. Well, they are guaranteed a very tiny drop, but it's almost inconsequential. This is the place where you're not going to get real good dispatch service from Prism. Over here on the entitled cores is the place where you're going to get excellent dispatch service from Prism, especially the vertical highs. So the charge to the operating system running in the LPAR is to run on only its entitled cores whenever it can. All right, so I've talked about weight, and I've talked about entitlement, and I've talked about logical cores, and I've talked about where to make changes on these things. I want to talk now about ways that things go wrong, the kinds of configuration mistakes that I have seen when people set up their CPCs. I said that the MONWRITE data lately had been showing me things that I didn't really care for, and I want to talk about a couple of the situations that I've seen. So the first situation that I've seen is something that I call unusable entitlement. I want to take a look at LPAR 13 in this table. This is an excerpt from a PerfKit report called the LShare Act report. What this report does is it shows us every partition that's activated and how many logical cores are defined in that partition, and then what the partition's entitlement is. If you take a look down here at LPAR 13, you can see that LPAR 13 has 22 logical cores defined for it, but its entitlement, according to the calculation scheme that I described a little bit ago, its entitlement is a little over 26 cores worth of power. So what we end up here with for LPAR 13 is 22 vertical highs, and then there is unusable entitlement left over, right? There's entitlement that was unable to be distributed to the other LPARs. Their logical cores are not as entitled as they could be because there's too much entitlement assigned to LPAR 13 compared to what it can use. So PerfKit tries to alert you to this. Out here in this column called core configuration, there's a letter U, and it means underconfigured. What this means is there are not enough logical cores in LPAR 13 to use up all of its entitlement. So this is the thing that you want to look for when you're evaluating your configuration. You want to especially check to see if you see any U's out here. I don't know if other performance products alert in this way, but PerfKit definitely does. Now, what do I mean by other partitions are deprived of entitled power? Well, in other LPARs, like LPAR 5, for example, maybe some of its vertical lows could have been vertical mediums or vertical highs. Maybe some of its vertical mediums could have been vertical highs if its entitlement had been larger. That's what we're trying to do here. We're trying to make sure that we don't have any places where there is unusable entitlement. Now, to correct this, we need to change some weights, and I think on the next chart I have an illustration of that. Okay, so solution one, the solution for problem one, in other words, is to change the weights. What I did here is I prepared a little table, a spreadsheet, pasted it in. I've got all of the partitions named here, their numbers of logical cores, and these are the weight from the previous chart. A lot of those partitions had weight 60. The LPAR that was grossly over entitled had weight 200, and then LPAR 02 had a weight of 10. So what the administrator did here was create a situation where LPAR 2 and LPAR 13 were completely entitled. There was more than enough entitlement for the number of logical cores. LPAR 2 has 1 core with entitlement a little bit over 1.3, and LPAR 13 has 22 cores with entitlement a little over 26 cores worth of entitlement. So what we want to do is we want to make some changes to the weights to preserve those two tuning choices, but let's dispose of the notion of having excess entitlement on those LPARs and spread it around. So what I did was I just made some very small changes to the weights on this CAC. I changed that 200 weight to 153. I changed all those 60 weights to a 59. I changed that 10 weight to a 7. And look at the result. LPAR 2 is still fully entitled. It has 1 core and entitlement of a little over 100, so we didn't change the dispatch experience for LPAR 2. Similarly, down here at LPAR 13, it has 22 logical cores and the entitlement is right about 2200. So every logical core in there is going to be a vertical high, just as it was before. But look at what happened to the entitlements of the other partitions. Instead of 800, this went to 848. In fact, all of these LPARs with 60 went to 848. And then look at what happened to these LPARs at the bottom. They had entitlement 133 and their entitlements went up. So what this does is it increases the entitlements in the LPARs that were under entitled without any harm to the partitions where we had previously had excess entitlement. So you want to look carefully at your weights to make sure that you don't make this kind of mistake. This is something that has been popping up in MONWRITE data lately, and I wanted to bring it to your attention. So the other problem that I often see is this notion of excess logical cores. And to some small margin, it's okay to have this, but what we want to avoid is egregious numbers of excess logical cores. And I'm going to show you why we want to avoid those. LPAR 3 has 11 logical cores, but entitlement of only 406. You can see that right here in the PerfKit LShare Act screen. 11 logical cores, its weight is 140. The entitlement is 406. So if we look at what kind of assortment of polarities would be given to LPAR 3, they would get 3 vertical highs, 2 vertical mediums of 53 each, and 6 vertical lows. In other words, about actually more than half of the logical cores in this LPAR have no entitlement. So out here on the right-hand side again, this column from PerfKit helps to call out for you or show you where there are partitions that are over-configured. That's what the O means. If you see an O out there, it means that there are more logical cores than the entitlement can power. The partition is over-configured to some extent. Now, the other thing I want to call to your attention is out here in the column called core total, this is the core busy for this partition. The partition has entitlement 406, but routinely it is using way over its entitlement. In other words, this partition is configured with too little entitlement for its workload, so it's having to make hay with unentitled cores, with vertical low logical cores. It is routinely using beyond its entitlement. Its space in the closet is entirely used, and it's eating into the space for its partner. And I want to talk about some of the reasons why that's a problem. So here's a graph where I tried to point out for you the LPAR 3's core consumption as a function of time. I produced this from PerfKit report called Interim LShare Act, and what I did was I just plotted the total core consumption as a function of time. You can see the timestamps down here on the bottom on the x-axis, and the blue bars down here represent entitled power, and the red stacked area on top represents unentitled power, the sum being the height of these peaks right here. So what we can see is that LPAR 3 is habitually getting its work done by running on logical cores that are completely unentitled. It's getting its work done by running on vertical lows. The reason this is bad is because lows don't really get a premium dispatch experience from Prism. They get to use power only when other partitions are not using their entitlement. So you can imagine that the power delivery to a vertical low can be somewhat erratic. And in fact, depending on what the other partitions are doing with consumption, a vertical low can get no power at all. It's not entitled to anything. So what do we learn from this graph? if there were just one or two red peaks in this curve and mostly the power consumed were down here in blue, I wouldn't be worried. But this partition is chronically getting its work done on unentitled power, which means that it is routinely exposed to the erratic dispatch behavior that a vertical low rightly can experience from Prism. So what are the hazards of running on entitled power? I wrote here, Prism doesn't guarantee a premium dispatch experience. In other words, a vertical medium or vertical low might sometimes want to run, but not be able to because the other partitions are using their entitlements. And when that happens, the workload in the partition suffers what we call suspend time. So I tried to graph here as a function of time the suspend time on every one of the logical cores in this LPAR. Suspend time is time the logical core wanted to run, but Prism didn't run it because usually the logical core is trying to use beyond its entitlement. And for vertical low, that means it's trying to use anything at all. You can see that some of these logical cores experienced suspend time above 20%, and that means 20% of the elapsed time that logical core wanted to run, but Prism didn't run it because there was no power available. That logical core was a low, say, and there wasn't anything in the cupboard. The load couldn't run because partitions that had entitlement were running instead. And this is bad for the workload. The workload gets delayed. All kinds of bad things happen when you have large amounts of suspend time like this. You definitely want it not to happen. So what are the consequences? When suspend time happens, what are the consequences for the various components of the system? Well, I've shown over here on the right-hand side of the chart that every layer in the stack, every layer in the service stack, the software stack, experiences consequences when this happens. Right now, I'm talking about the consequence for the guests that are running on our control program. The guests have an API available to them that lets them kind of give away their CPU time to the other virtual CPUs in their configuration. This API is known as Diagnose 9Charlie. Let's say we have a Linux guest that's a four-way, and one of the virtual CPUs in that Linux guest detects that one of its brethren virtual CPUs in the same configuration is not getting its work done. The way that the guest can influence that is to issue this API called Diagnose 9Charlie to tell the control program, hey, stop running me and run my sibling virtual processor instead, because the sibling is trying to make progress. His failure to make progress is holding me up, so I want you to give the rest of my time to that sibling who's impeded. The use of that API called Diagnose 9Charlie is journaled in our monitor data, and we can see that right here, one or more of the virtual processors of this guest experienced a peak in its use of Diagnose 9Charlie, and we can trace this exactly to the fact that the logical processor on which that guest was running was suspended. I've got over here on the left-hand side, one or more virtual CPUs of this guest were stuck on logical CPUs that were experiencing suspend time, and their friends, their brethren virtual CPUs in that guest, tried to unstick them. 9Charlie is a terrific source of overhead, right? It drives excess simulation overhead in the control program. It drives excess looping in the guests. We want the guests not to have to do this. So we want to make sure that we configure our systems in a way that doesn't cause suspend time. So now we've gone down one layer in the stack. Here we have consequences of suspend time for the control program itself. Right? The control program has spin locks also, and it issues Diagnose 9Charlie down to Prism. Here we've got a situation where we've got a partition running on entitled power. The CP Diagnose 9Charlie rates are usually 0. But when CP itself has to use Diagnose 9Charlie, CP efficiency drops. So this is pure overhead as well. Here we're inducing overhead in Prism. The control program itself is using 9Charlie, and there's a peak right there. It lines up with a suspend time peak. So that's what we're talking about. The entities on the right-hand side of this graph are logical processors in the partition, and those logical processors are using Diagnose 9Charlie down into Prism, and that creates overhead. All right, so what about the consequence for Prism of suspend time? What kind of overhead gets induced down there? Well, the control program is doing 9Charlies down to Prism because the control program's logical processors are experiencing erratic behavior. And what that does is that induces excess CPU time consumed in the Prism hypervisor. What I've got here is a graph of LPAR management time as a function of time in this very same workload, and you can see that in places Prism is using 35% of a logical core to do LPAR management time, which is basically scheduling and dispatching of partitions. If we had a well-configured system where entitlement was set so that we didn't have to do all these 9 Charlies and we didn't experience suspend time, the Prism overhead would be a lot smaller, and that's CPU time that can be returned to you for use by your workload instead of overhead time spent in the Prism hypervisor. So yet another consequence of suspend time, something we really want to avoid. Now, I want to talk a little bit about the cache impact of using unentitled power. I told you that there are impacts at all of these different places in the stack. There's impact on the memory cache also. Unentitled logical cores have a preferred dispatch location. Your vertical lows have a preferred location, just like your highs and your mediums do. But they are exposed to being dragged elsewhere to be run. Let's suppose that we have a partition that's homed in drawer 1. We've got a logical core over there that needs to be serviced. Prism tries to refrain from doing this, but occasionally it will find unused power in some other drawer, and it'll use that unused power to go drag that logical core across drawers and dispatch it. When that logical core runs in a place that's not its home, there are cache effects. That logical core does not experience particularly good CPI because the cache over in drawer 4 is not hot for that LPAR. And similarly, when that logical core runs over in that far drawer, it corrupts the cache of the partitions that are actually homed there. So we don't want that to happen. What ends up happening is that we increase CPI for both the partitions that are homed over here in drawer 4, and we increase CPI for the logical core that got dragged over there. And that increased CPI, increased cycles per instruction completion, is just overhead that we could avoid if we could avoid using vertical lows. So the solution to all of this, of course, is just to adjust something. Are the weights too small? And the way you can check that is, are these partitions getting their work done on entitled power, or rather, do they look like that stacked column chart a few charts back where the partition is chronically getting its work done on unentitled power? If the latter happens to be true, then you need to adjust the weights. You need to set the weights so that the partitions have enough entitlement to get their work done on entitled power most of the time. And if you are not able to make all partitions get their work done on entitled power most of the time, then you probably don't have enough physical core power in the KEC. Now, the other thing to look at is, are the logical core counts too large? You know, this partition LPAR 3 is entitled to about 4 cores worth of power, but it has 6 vertical lows. Does it need to have 6 lows? Does the core count really need to be 11 here? Maybe it should be smaller, and you can evaluate that by looking at core utilization as a function of time. I had a graph of that a little ways back. My friends over in Prism development tell me that there really ought to be no more than 1 to 2 vertical low logical cores per partition. So as you're setting up your KEC and you're comparing your core counts to your entitlements, you might want to keep that in mind. Now, what I tried to call out in this LSHAR Act report was LPAR 2 has entitlement of 2467, but it's really using only 15. In other words, entitled to 24 cores worth of power, but using on average only 15 cores. So maybe there's an opportunity here to move some weight from LPAR 2 to LPAR 3 to improve the situation for LPAR 3 without impacting unduly what's going on in LPAR 2. So let me give you some techniques for dealing with this. One of the things that I see is that people tend to assign the weights with no particular heuristic in mind. Sometimes they just make up weights out of thin air and say, oh, I'll just make partition Fred have weight 35 and Barney have weight 19, what have you. And we don't want to do that. We want to be somewhat methodical about what we're doing here. Some people try for the sum of the weights to add up to some interesting cardinal number like 1,000. And that makes the weights portray percentages of the shared power pool, like I showed on the pie chart a way back now. And people who do this, who make the sum equal to 1,000 or the sum 100 or what have you, they think this is helping them because they can look at the weights and they can see the percentage of the shared power pool that that partition is allowed to use whenever it wants. In other words, the weight portrays the percent. But in my opinion, both of those techniques hurt us because what we can't immediately see is the entitlements. What we want to be able to see when we look at the weights without having to dig through a lot of reports and performance report listings is we want to see the entitlements right away, because we want to compare the entitlement numbers to the logical core counts and come to some understanding about how many lows we've got out there, and maybe we've made an adverse configuration in some fashion or another. So what I do is I make the sum of the weights equal to 10 times the number of shared cores. So you can see this CAC has 45 shared cores, so I made the weights add up to 450. And what that lets me do is look at the weights right away and see, oh, the entitlement must be 16.1. This entitlement must be 6.4, and so on, because the sum is exactly 10 times the number of shared cores. And you can see that's borne out over in the column here on the right. So use weights that immediately inform you about entitlements. That's one of the techniques you can use. Another technique you can use, of course, is don't be afraid to change LPAR weights when you need to. Here we are looking at our friend, the Change Logical Partition Controls screen. There's no reason to be, permanently linked to all of these weights that you decided last year or last month or what have you. Make changes when you need to change them. Pay attention to which partitions are using unentitled power, and if they're routinely using it, you probably need to make a change. Another technique is if you're on prior to 7.2, if you're on 7.1 or 6.4 or what have you, those releases were too aggressive in unparking vertical lows. And excessive use of vertical lows contributes to suspend time, which we've seen is bad in a number of ways. So if you are on 7.1 or earlier, this chart should probably say earlier, I want you to go configure to use medium unparking. Medium unparking does not use vertical lows if it doesn't have to. So in other words, if the workload will fit on your entitled cores, CP will shut off the vertical lows. And this is the configuration knob you want to use. In the config file, you can code SRM unparking medium, or if you'd rather manage this by a CP command, you can issue CP set SRM unparking medium. If you're on 7.2 or later, as long as you didn't override the defaults, you're going to get medium unparking. We made that change in 7.2. So best practices: know your workload's needs for power. Make sure you observe the way your partitions are running. Set their entitlements to match the needs of the workload. Use weights that immediately portray entitlements. Use only 1 to 2 vertical lows per partition, and then pay attention to the LPAR Act report or your performance products equivalent to see how it's going. Watch the relationship between entitlement and use of power to make sure that your partitions are running on entitled power most of the time. Run with medium unparking, and don't be afraid to make changes. I once encountered somebody who had the weights set on their CPC, it was a Z14. I said, why did you do this? And the reason was, well, the guru who configured us when we were a Z10 said that these needed to be the weights. Don't be that person. Measure your system and make changes as you have to. So let's talk about some tools. One of the tools that is out there to help you with all of this is out on our VM website in the performance tips section. There's a URL you can visit, and it's right here on the bottom, that is an LPAR entitlement calculator. You can do what ifs with this tool. You can fill in the names of the partitions that you're experimenting with, the number of logical cores that you want to have in them and what their weights are, and then the number of shared physical cores on your CAC. And the instruction says, fill out the form, then click here, and you click the calculate button. I will tell you the CGI keeps no record of what you type in. It's really just here for you to use to try some what ifs. So let's say we wanted to check out what would happen if we had 4 partitions with these weights and that many shared cores. We click calculate, and what happens? Well, you get a table back that looks like this. It's got all the partitions named, the cores, the weights that you typed in. It calculates all the entitlements for you. It shows you how many vertical highs would be in each partition, how many vertical mediums or horizontals if you were running horizontally, and then what those mediums entitlements are and the number of lows. And then if you committed the sin of unusable entitlement, that shows out here in red on the right. And you can see that the configuration we supplied shows that Wilma ended up with unusable entitlement. So something's wrong there. Either Wilma doesn't have enough cores or Wilma has too much weight or what have you. So if you want to do what ifs and experiment, you can certainly use the LPAR entitlement calculator, and its URL is on that previous chart. There's also a tool on the VM download library, something called CalcEnt. This runs off of a MONWRITE file. If you have a MONWRITE file, you can feed it into this calculate entitlements tool, and it'll draw for you what all of the vertical high, medium, and low situations are for all of your partitions. It also draws the entitlements, tells you how many logical cores there are. This is slightly better than the PerfKit LPAR Act report in that it's got the core polarities right out here on the right-hand side. So if you have a MONWRITE file laying around, you can check to see how the current situation is. Now, there's another tool out there. If you have a Z16, there's a tool out there called D0R16 Top, which portrays the machine topology. The MONWRITE data on the Z16 has been upgraded to show you where all the partitions are placed in the physical topology. You get a MONWRITE file, you run it through this tool, D0R16 Top, and it'll show you where all the physical cores are in the machine and where all the LPARs are homed in the machine. This is a good tool to use to see what we mean when we say that Prism places partitions so that they don't collide with one another in the topology, and if you run on your entitled cores, how much better life can be for you. So you need a Z16 and you need 66532 to get that. All right. The last thing I want to talk to you about is cores and CPUs. I've talked about cores an awful lot. If you're running SMT2, you really need to understand the difference between a core and a processor. I've included some attributes here for cores. You configure the partition with logical cores. The machine has physical cores. In the image activation profile, you're giving the partition cores. And then when you turn on MT2, you're splitting each one of those cores into two processors, the IFL cores anyway. The CPs and zips and stuff don't get split, but the IFLs do. Utilizations in these PerfKit reports are core utilization. This is the thing that drives suspend time. This is the way utilization racks up on physical cores and what have you. You run MT2, each core has two CPUs in it. These PerfKit reports, CPU, proclog, and so on, those portray CPU utilization. You need to be aware of the difference between core utilization and CPU utilization. And there are a couple of articles here that you can read. This chart attempts to illustrate for you that when Prism dispatches a logical core in MT2, which is portrayed by the blue line here, the square wave indicates that the core is dispatched for this period and it's not dispatched outside. Those processors on that core go in and out of wait state. Processor 1 maybe runs some of the time, processor 2 runs some of the other time, so you can see that CPU utilization and core utilization are not the same. That's why I included the previous chart to show you which reports are core utilization and which reports are CPU utilization. So that's it. Know what the LPAR weight is and what it means, what it controls. Know where to change it. Know about the image activation profile. Know about the change LPAR controls screen. Know how to calculate entitlements. Make weights that immediately tell you what the entitlements are. Understand the relationship between entitlement and logical core count. Understand the common pitfalls, which are basically too little or too much weight for the number of logical cores in the partition. And most important, don't be afraid to make changes. Tune your KEC. Watch what the partitions are consuming, and don't be afraid to tune up those weights or change those logical core counts to make your KEC run well. So I included some references at the back of this deck. These are all articles that you can read on the VM webpage. They talk about the various unparking models and the entitlement calculator, what VM hyperdispatch is all about, how to talk about SMT in a way that your friends will understand you, what utilization is like in an SMT world, what the difference is between core utilization, CPU utilization, and what have you. So again, my name is Brian Wade, and I'm hoping that I have shown you some things about how to stay out of trouble with LPAR weights.
Thanks for watching. If you enjoyed this video, don't forget to like and subscribe to see more videos like this one. Have a suggestion for another video topic? Feel free to leave a comment below.